One of our many, many objectives for this section was to determine a function's symmetry, either odd or neither. So what we did on Friday was we talked about you put a negative x into the function algebraically, and you see what happens. If putting a negative x into the function just gives you the original back, that's because it's even and it has symmetry with the y-axis. If putting a negative x into it gives you the exact opposite, then it's odd, and that tells us that it really has, well, symmetry through the origin, which is 180-degree rotational symmetry. And if it's a mixture of those two things, then it's neither. So for D, we will go ahead and put in a negative x and see what happens. So that will be negative 2 times negative x to the 5th plus negative x to the quantity cubed plus 6 all over 3 times negative x quantity squared plus 4. A lot of negatives there. So on the top, well, negative x to the 5th will be negative x to the 5th. And so the negative and the negative here are going to cancel each other out, and that'll give us a positive 2x to the 5th. Here, a negative x to the 3rd is going to be negative x to the 3rd plus 6. On the bottom, when you square a negative x, you just get x squared, so 3x squared plus 4. So this is the part where we stop and say, okay, we put a negative x in, did we get exactly the same thing? Did we? No. We put a negative x in, did we get exactly the opposite of what we have up there? No. So this is a neither. But again, we have to write what we just did, which was checking for that symmetry. So, I forgot what this one was called. Y of x. Good thing they're sturdy. Y of negative x does not equal y of x. Or this would have been. Why isn't it odd? If it's odd, everything in the numerator would have to be the exact opposite of what we saw before, because it's like multiplying it by a negative 1 over 1. But every term is not going to do that. Because we should get positive 2x to the 5th minus x to the 3rd minus 6 if that happens. And this was not a minus 6. So it's because of that constant behind that odd function that's not promoted. So that's how we say this in notation. Y of negative x didn't come out to be the negative of the original function. So that gives us a neither. So what we're looking for is the exact same thing, then we write even. Or if the numerator, and we kind of discussed this on Friday, I don't know if we did it in this class, but I know in other hours, so let me go back over that again. If we're going to multiply this by a negative 1 and we want to know what to expect, remember, it would have to be a negative 1 over a positive 1. Because if it's negative 1 over negative 1, well, then we're just multiplying by 1, and that doesn't do anything. So it would have to come out to be 2x to the 5th minus x cubed minus 6 for our numerator in order for that to happen. We just didn't get a perfect match. It didn't happen. So let's look at H. This is interesting. Radicals. First off, this problem drives me nuts because it's not simplified. But we're not, that's not our job. Our job is not to simplify. Our job is to figure out, if we put a negative x in there, what's going to happen. So, f of negative x equals negative 3 cubed roots of 8 times negative x. Well, that would be negative 3 cubed roots of negative 8x. But we never leave negatives under the radical, no matter what. The 8, we have to leave there because we want to compare it to the original, but never the negative. So what we would do is this. Negative 3 times the cubed root of negative 1, and then the cubed root of that 8x would stay right there. Well, that's, of course, negative and a negative, which makes a positive. So we put that negative in there, and then we did the simplifying just focusing on the negative, because that's what we need to focus on for symmetry. And we get that. Even, odd, or neither. Did we get exactly the same thing? It's not even. Did we get the opposite of what we started with? It's odd. So capital F, negative x, was the opposite of our f of x, which makes this odd. Makes it odd. So, again, I was just trying to keep it looking like the original. The only thing that we are concerned about is that negative. Did it go somewhere? Didn't it go somewhere? Or is it kind of everything's mixed up and it's right? Wowee! Look at that little one there. T of negative d. All right, so negative d, 2/3 over square root of negative d squared plus 4. Well, I like the denominator because it's not a lot of work. Square root of d squared plus 4. So that's all good. You have to think, okay, what would I do with that negative up there? Believe it or not, it's a lot like last time we just did. And that's because this is a cubed root. So the cubed root of negative d, we would say, hey, that's the cubed root of negative 1. What is the cubed root of negative 1? Negative 1. But then, we have to square it. So if we square that negative 1, it's going to come out to be positive. I'm going to go back to writing it the original way. Oh, I can't scroll up to the beginning. I guess you guys can see it in your packet anyway. So is this one even? Is it odd or is it neither? Even? Yeah, we put a negative in there and we got right back to the original. So, what was the name of this thing? Was this T of D or something? T of D? So that last notation, that's our summary of what we've just found out. Now, there's even another. How do you feel about those? 4, 3, 2, 1, 0, man. Just even odd. Okay. So some people it's coming back from last week, and others it'll take a little bit. So certain things we know. We know none of the signs change after you put a negative x in there. That makes it even. You just get back what you had originally. That makes it even. That means it's symmetric to the y-axis. That's the whole reason that that happens. If all of the signs change, that makes it odd. So if we're multiplying it all by a negative 1, that's when we get odd. Some change, some don't. Yeah, that's going to be our neither. Kind of mixing and matching there. Now, I'm going to go back to the last page. You can stay where you are for a second. So I want us to look at what we had for E and F to get back to this. If we separate these and we say m cubed, that's a polynomial. On its own, it would be odd. 3 minus 2m squared on its own would be even. So when we had odd and it was divided by even, our answer came out overall as odd. And then for F, we had odd, 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 and down here, odd and odd. But that didn't come out as odd when we got done. That came out as even. So this has a lot of parallels with positive and negative. Do you see that? You can think of odd as being a negative and even as being a positive. A negative and a positive give you a negative, so it's odd. A negative and a negative give you a positive, so it's an even. So you can break quotients apart and kind of get a feel for what your final answer is going to be when you're just looking at just the numerator and just the denominator. And that's what this stuff is for. So even over even. Okay, well, even is like positive. So positive over positive is positive. It should be even. How it should work? even over odd, odd over even, negative over positive, positive over negative should be negative, so that should be odd. Odd over odd, negative over negative should give us a positive. Even. But that doggone neither shows up. So when we have the quotients, which of course are going to be the hyperbolas, we can tear those apart and think of them separately. And sometimes that makes it easier to figure out whether or not it's even or not. Although I don't think the whole process is that big of a burden anyway. You know, you're just putting a negative x in there and you're seeing what happens when you get done. So now we're going to move on. And when you see asymptotes, hopefully you're saying to yourself, I already know how to find the vertical asymptotes. Well, yes, those are really important. That is usually the first thing I go after when I'm trying to graph a hyperbola. So 2x squared, I would factor 2 plus x, 2 minus x for my denominator up here. And I would say my vertical asymptotes are at x equals negative 2 and x equals 2. And I would go over and put those little helper lines right on here. But the next thing I usually do is the horizontal asymptotes. And we haven't talked about those yet. So I'm going to skip that step for just a second, because after that I'd say, what would be an easy point that is on my graph? I mean, I know where it's not going to go. Where is it going to go? And that would be by saying, well, when can I make things 0? I mean, can I make this number 0 somehow? And absolutely I can if I put a 0 in there. So that means this is one of the points on my graph. Now, last year when we did these, what we did was, I know in my class I explained the process of, bless you, getting those horizontal asymptotes. And I'm going to do that today with a little bit of calculus too. But we also said, here's a slip of paper. If this doesn't work for you at this time, if you need another year to think through it, here's what we're going to do. You're going to memorize it. If the degree of the top is less than the degree of the bottom, the horizontal asymptote is y equals 0. If the degree of the top equals the degree of the bottom, you take the leading coefficients as a fraction, and that's where your horizontal asymptote is. If the degree of the top is greater than the degree of the bottom, then you don't get one. There is no horizontal asymptote. So using that as a rule, I would rewrite this so that my denominator is in standard form. And say, well, the denominator and the numerator are both degree 2 polynomials. So that means I'm supposed to make my little fraction right here and use that as my horizontal asymptote. Well, that's 2 over negative 1, which is negative 2. So y equals negative 2 would be my horizontal asymptote. Now, here's the thing to remember about horizontal asymptotes. They're not going to be crossed as you go to the left forever. They're not going to be crossed as you go to the right forever. But sometimes they get crossed in the middle. Sometimes we have a portion of our graph that actually crosses that horizontal asymptote. The cough dropped in there. Okay. And that's just hyperbolas. Hyperbolas are weird. They just do those things. So what we're trying to do is we're trying to get as much information as we possibly can without having to actually grab the graph and calculate it. And then, well, hopefully we'll have enough. You know, maybe to just make an itty bitty little table and have an idea of what's going to happen. And we wouldn't need the graphic calculator. So now, could we have found these algebraically? Well, I already did. And yes, you guys could too. I know that. You're used to looking, hey, it's division. I can't divide by 0. What would make me divide by 0? Boom, those are your vertical asymptotes. Unless they cancel on the top, then you know that they're going to be poles. But we have been avoiding the horizontal asymptotes for a little while. And that's because my hope is you don't just memorize that. I'm going to put it up there and I'm going to give you time to write it down. My hope is you don't have to memorize that. My hope is when I explain how the horizontal asymptotes come to be, that it'll make total sense and you'll say, oh, I wish I'd have figured that out a long time ago. Then I wouldn't have had to memorize. Because last year I know I gave my Algebra 2 students a little cheat sheet with this on it. They're not allowed to use it on the test, but our brain is such a marvelous little machine that if you have to look something up on paper more than 3-4 times, your brain says, I'm going to memorize this whether or not you like it or not. I'm sick of looking this up on paper. Again, horizontal asymptotes are one of those things. Somebody in first hour said, why do we even call them a horizontal asymptote if they can cross it? Isn't the definition of an asymptote a line that you approach but never cross? And I said, yeah, that's the problem with horizontal asymptotes. Sometimes they get crossed, usually for the middle portion of the graph. So they don't fully meet our definition of what we would think of when we say asymptote. More time. Now, does anybody still need more time? All right. So here's the deal. When we start talking about calculus, we start talking about what do things approach as a limit? Where do they go? And that often involves our thinking about that number right there, infinity. If I ask you to give me a number to represent infinity, can you do that? No. It goes on forever. It keeps getting bigger and bigger and bigger. So there's infinity. And we know infinity is huge. And I come along and I say, I'm going to have you add 2 to that infinity. That's a lot like your very, very environmentally friendly friend that you take to the ocean. And you're standing at the ocean and your friend says, man, I can't believe this. Every year, because of our behavior, these levels in this ocean go down. All the time. They're going down all the time. And you say, well, what are you going to do when your friend says, I know what I'm going to do. Every day we're here, I'm going to come to the ocean and I'm going to spit in it to raise the water levels. That's what I'm going to do. There's water in me. I'm going to give it to the ocean. That too is spitting in the ocean. It is not making a bit of difference. None. That's spitting in the ocean. We don't need it. It doesn't do anything. In fact, that 1,000 is spitting in the ocean. It is. You're really not adding anything to infinity. It's infinity. It's more of a concept. It is. It is more of a concept. So now we're going to use that concept to think about these horizontal asymptote rules that we have. The first one said, if the degree of the top is less than the degree of the bottom, it's y equals 0. I don't want to memorize. So here's what I think. What they're asking me is, what is the behavior of this graph as I go to the right forever or as I go to the left forever? So this is going to be infinity over infinity squared plus 3. The 3 is doing nothing. It's infinity squared, for goodness sake. I couldn't care less about that plus 3. That's spitting in the ocean. So now I'm down to this. And I realize, well, if I treat it like a variable, I mean, that's really just going to be 1 over infinity, because that's a 1 and we could cancel one of those out. So this number down here goes from 1/2 to 1/4 to 1/8 to 1/16 to 1/32, etc. I want you to show me with your fingers in the air in front of you 1/1000th of an inch. Impossible, right? because at some point your fingers want to touch each other, and that's because it's going to approach nothing. It's going to approach 0. As that number on the bottom gets bigger and bigger and bigger, we get closer and closer and closer to 0 as a limit. So that's why when we have the degree of the top less than the degree of the bottom, it's y equals 0. Now, if we have a problem where we have the same degree on the top and the bottom, oh, your last one looked like this. That's a good one to use right there. Looks like this. So we use the same kind of thinking, and we say, okay, so this would be 2 infinity squared over negative infinity squared. I'm not writing down the plus 4, because that's fitting in the ocean. Well, it's infinity squared, and it's infinity squared. Those will cancel each other out. And I'm left with those leading coefficients. 2 divided by negative 1. That's why that works. So then there's that one last situation where your degree of your numerator is greater than the degree of your denominator. Let's make it real basic right here. We realize, all right, well, infinity cubed, infinity squared. Okay, but if I do the canceling here, I'm left with infinity, which is not a number, because it's going to keep going, and it's going to keep going, and it's going to keep going. So that's why when you have a degree of the numerator greater than the degree of the bottom, denominator, you don't get one. They don't get one. So it's all about thinking in terms of infinity versus thinking in terms of the x's. So that way, you wouldn't have to think this. That way, you could just think through it each time. What is this going to be? And think about it that way. So, this says a little bit more than that. We won't find spitting in the ocean up here either. The line y equals b is a horizontal asymptote of the graph of the function y equals f of x if f of x approaches some number, some limit. Now, this should look really familiar right here because you did these types of limits for end behavior in Algebra 2. The limit as x approaches negative infinity of your graph f of x equals, what does it equal? What is it approaching as you go to the left forever? And then the limit as x approaches positive infinity of your graph is b if, as you're going to the right forever, you are actually approaching an asymptote. And remember, that's what horizontal asymptotes are about. It's about as you go to the left forever and you go to the right forever. The middle stuff, it just happens. You know, it just does. That's hyperbolas. But we want to see what's going on to the left and what's going on to the right. And then this piece we'll end up coming back to. Right now, it might be a little overwhelming with all the new stuff about limits, but the line x equals a is a vertical asymptote of the graph of the function y equals f of x. If f of x approaches some limit, which means positive infinity or negative infinity, because we're talking about going up or down, as it approaches a from either direction. What on earth is this then? This is telling us we're not just going to talk about those vertical asymptotes anymore. We're going to say, as our graph comes in from the left, where's our graph going? Is our hyperbola going up to positive infinity, or is it going down to negative infinity? And then as we approach our vertical asymptote from the right, is our graph going up, or is it coming in and going down? So when this has this little limit x approaches a negative, that means from the left side. As you're getting closer to that vertical asymptote, what's happening? Is it going up for positive infinity or down for negative infinity? And then as x approaches a from the positive side is from the right side. From the right side. So not just vertical asymptotes anymore. Trying to describe the behavior of the graph as we approach that. Like I said, we'll ease a little bit more into that. We've really got enough to keep track of right now, but know that that's coming. So this says identify any horizontal or vertical asymptotes of the graph. And I wish the picture weren't there. I would really want to do this algebraically and say, okay, I'm going after the vertical asymptotes first. So I need to come up with two numbers that multiply to -2 and add to -1. What are they? So that's going to give me my vertical asymptotes of what and what? 2 and -1. Stay with us, Brianna. So my hope is that their graph over there matches that. So I go over, x equals 2, right there. 1, right there. 8. So far, so good. It's looking good. All right. Then I say horizontal asymptotes. What do I have for horizontal asymptotes? Well, let's see. This would be infinity over infinity squared, and that would be spitting in the ocean. It really would. What we care about is those powers of infinity, because those are what are going to give us the highest numbers. And they're going to take over. They really are. So if I do that, I'm going to have infinity over infinity squared, and that'll reduce to 1 over infinity. And that's 0. So this should have a horizontal asymptote of y equals 0. And that was where a couple of first-hour people lost it. Does everybody see it crosses in the middle part? It does. It's a hyperbola thing. There's nothing we can do about that. But notice, this portion of the graph is going to approach y equals 0 as you go to the left forever. And this portion of the graph is going to approach y equals 0 as we go to the right forever. So that's what horizontal asymptotes are trying to tell us. Is, hey, out here, this is what it's going to do. Don't worry about the middle. Weird stuff happens. But worry about the right and the left. So, what we're talking about is really end behavior. As you go to the right forever, as you go to the left forever, as you go up forever, as you go down forever. A horizontal asymptote gives one kind of end behavior for a function because it shows how the function behaves as it goes off toward either end of the x-axis. So to the left forever, to the right forever. Not all graphs approach lines, but it is helpful to consider what does happen out there on both ends. We illustrate with a few examples. So we have 4 equations, and we should be able to match these up to the graphs down below simply by knowing horizontal asymptotes and even versus odd. That's all we should have to do. So I'm going to show you the first one here. Match the functions with the graph in figure 1.35 by considering their end behavior. All graphs are shown in the same viewing window. So the first thing I would look for is vertical asymptotes. And don't get any. None of them. X squared plus 1 is not factorable. And if I tried to solve it, x squared plus 1 equals 0. Move the 1 over, x squared equals -1. Oh, it's imaginary, I can't do that. So next thing I do is think infinity over infinity squared. 1 over infinity. All right, so this graph, as we go to the left and right forever, should approach the x-axis, because that's the equation for the x-axis, y equals 0. Even versus odd, well, if I put a negative in here, it's going to stay negative, but if I put it down here, it'll become positive. So this will truly be the opposite of what it was to start with. So I need one of these 4 graphs to approach the line y equals 0 as it goes left and right forever, and I need it to be symmetric to the origin. Well, symmetric to the origin has me down to 2 and 4, but only one of these 2 graphs is going to approach the x-axis as it goes to the left and right forever. That's this one. That behavior as it keeps going. So that would be a little Roman numeral 4 action up here for this one. That's what matches that. So using that behavior, we should be able to match up the other 3. And I'd like you to get started on that, which I know you already. The graph that you can see is getting closer and closer to 3 as we go to the right and left forever. So that one has to be the 3. And then for the last 2, you look and you say, well, that'll be infinity cubed over infinity squared. So if I cancel, it's going to be infinity. That's it. We get a horizontal asymptote. So how do I tell? Even versus odd. Even reflected over the y-axis, and then odd reflected over the origin. So if I put a negative x in here, this is going to be negative. If I put a negative x in here, this is going to be positive. Or you can think odd, even, that's going to be odd. So of these two that are remaining, which two has symmetry with the origin? That's this one, right here. So process of elimination, it has to be the first one, but let's not go by process of elimination. This one would be, again, with infinity, we're going to end up with infinity squared on the top, so we don't get a limit for a horizontal asymptote. But if we think about negative x and negative x, even and even, that should give us an even in the end. And this definitely is reflected over the y-axis. So that's one. Thank you, partner. There one. I would like you to 43210 me, please, on horizontal asymptote. Whether or not it's you've already rememorized the little chart, or if you're using limits with infinity. So what we're going to do now is